class. Welcome back to our tutorial section. And today we are going to talk about RTOS. Okay, we're going to talk about RTOS concepts in our tutorial 5. Right. Before we start, I'm going to I'm going to take your attendance first. So let's see. We have 15. I think everyone's here. I think everyone's here. So just check. Everyone is here. Okay. Stage. Oh, hold on. Yeah. Okay. Thanks for reminding me. I forgot to lower my mic. Okay. So everyone is present. Excellent. Full attendance. Very good. Okay. Now, we have let's look at our tutorial question. So, again, tutorial 1 is on introduction to microcontrollers. So you looked at what were microcontrollers in tutorial 1. Tutorial 2, we talked about software development, how you write programs in C. Tutorial 3, we looked at the processor architecture, right? Assembly and interrupts. Tutorial 4, you look at memory system. So tutorial 1, 2, 3, 4, basically we were talking about the Cortex-M processor architecture and how to write C programs, right? Now we go to tutorial 5 where we will look into using the real-time operating system and real-time system concepts. Okay, so let's look at this tutorial 5 now. And as usual, your tutorial is mostly theory questions. So I'll just go through a few questions with you, let you get a hang of these theory questions. And then we will try out some exam type questions. Okay, okay, let's look at the first one. Describe how a super loop program structure handles time critical and non-time critical program functions. So let's try to understand this question first. Okay. So the question says that the question is asking you to describe a super loop program structure. Now, first of all, how many program structures do we have? How many program structures do we have? So you have three general types of program structures, right? Three types of program structures. When you develop a program for a microcontroller, there are basically three types of program structures that you can use. The first type is called a super loop. So a super loop is, if this is your main function, int main, okay? This is your main function. So normally in your main function, the first thing you do is you need to initialize something, like initialize the hardware. So I just call initialize function in it. Let's say we have this function, initialize the hardware. Then after you initialize the hardware already, we are going to have a while one loop. Now, why do you need a while one loop? Because we are running a program to control a process. Okay, we are running a program to control a process. We are not doing information processing. If you write your MATLAB program, or you write your C++ program last time, you are actually doing some information processing. Okay, that means you feed the program with some data. The program will go through a series of computations and give you a result. End of program. That's all. Because it's not controlling anything. It's just doing some calculation. But for microcontrollers, our program needs to control something. To control something, the program needs to run continuously. Okay, the programmer needs to run continuously. So you have to put your code inside a while one loop. We call this while one loop the super loop. Okay, we call this while one loop. This is called our super loop. Okay, super loop. It is the loop that covers all the code that you need to run continuously. So it's super outside all of it, a super loop. So let's say I want to do three things. Let's say I want to do three things. So this is my task A is a function. Let's say there is some code inside this function. I call task A to do something, right? Then maybe check the value of the sensor. If the sensor exceeds a certain value, then I need to do something. Okay. Then I got task B. Task B is maybe I'm checking whether the user got pressed a button or not. If he got pressed a button, then I need to do something. Okay. Oh, typo. Task B. Then I got task C. Let's say task C is to check whether there is any data at the serial port. So I'm expecting some data to come in at my serial port. So I use task C to check whether there is any data or not. And then I'm going to do these three tasks once every 100 milliseconds. So I'm going to delay 100 milliseconds. I call this function. Okay, so the what we're doing here is pretty obvious. I want to do three things at the same time. I want to check sensor value. I want to check button press. I want to check got data at the serial port or not. And I'm going to do these three things every 100 milliseconds. So I put them inside a super loop. Now, what's the problem? Okay, the problem with super loops. The problem with super loops is a problem. What is the problem? The problem with super loop is number one, there is no priority. There is no task priority. You see, all the tasks are inside the super loop. So all these tasks, they will run one after the other. In other words, they all have the same priority. Now, tasks cannot have the same priority one. Normally, some tasks will be more important than the others. What do we mean by more important? When a task detects something happening, it needs to respond immediately, and its response may be more important than the other task. For example, in your car also, in your car, you got the button to wind up or wind down your window, your side window, right? You got the button to control your side mirrors, and then you also got the brake pedal. So I ask you, which button is the most important? Obviously, it's the brake pedal, right? Nowadays, we have electrical brake pedals. It's not mechanical anymore. Last time, mechanical brake pedals, when you press the brake pedal, you are mechanically linked to the brake pads. Right? Nowadays, electric cars, your brake pedal is just a button. When you press the button, then you will activate the brake pads to uh, have friction with your wheels and reduce the speed of your car, right? So obviously, which is more important? When you press the button for the brake pad, you press the button to move your side mirror, or you press the button to wind down your side window. Obviously, the brake pad button is the most important, right? So all tasks they will have different levels of importance one. But Superloop doesn't support this because everything has same priority. That's the first problem. The second problem with Superloop would be the task interfere. The tasks they interfere with each other, right? The tasks they interfere with each other. Why do we say they interfere with each other? You see, when you run task A, you are checking whether the sensor got detect anything. If the sensor didn't detect anything, then task A will run very fast. Then it's task B already. Task B is checking whether the user got pressed a button. If the user didn't press anything, task B will run very fast. You go to task C. You check got data at the serial port. No? If no data, task C will also run very fast. Okay, so the program is very fast. And then you delay 100 milliseconds and you do it again. So quite accurate. We are doing this every 100 milliseconds. But imagine the case of if task A, the sensor detects something. So you need to run the code to respond. That code might take some time to run. Task B, the user pressed the button, so you have to run the code to respond for button press. That code might take some time to run. So task C also, if it detects some data at the serial port, then you need to extract that data. What if there is a lot of data? So task C may be running for some time. And when task C is running, A and B cannot run. If task C takes a long time to run, then A and B will have to wait a long time. And even though the user press the button or the sensor detects something, there will be no response because the processor is still running task C. So tasks that interfere with each other, this is not good. Okay? That's why we don't use Superloop for more time critical stuff. Only simple programs we use Superloop. Okay? And then the third problem is your loop uh, loop iteration, your loop execution time. No, don't say loop iteration. Your loop execution timer is not constant. Okay, you see here, I'm under the understanding that A, B, and C will probably take a few hundred microseconds to run. Okay, A, B, and C probably take a few hundred microseconds to run, very fast. So I nicely get 100 millisecond delay between each loop execution. But what if for A, B, and C, they need to do their stuff? So A may take a few milliseconds to run. B may take a few milliseconds to run. C maybe take tens of milliseconds to run. So depending on whether A, B, and C their conditions are true or false, the loop execution time will change. So we cannot make the loop execute periodically every 100 milliseconds accurately anymore, right? That's a problem because the time will change, right? We cannot base it on the time taken to run the task anymore, right? So this is a problem. Now, how do we solve this problem? We solve this problem by uh, using a foreground, the second program structure. So the second program structure is called foreground background. Okay, this is the second program structure. It's called foreground background. So what is foreground? Foreground is actually your ISR code, right? Background is your super loop code. Okay, so we have two types of interrupts. We have two types of interrupts. We got event triggered interrupt, and we got time triggered interrupt. What's the difference between event triggered and time triggered? Event triggered interrupt is, for example, uh, you have uh, you have some hardware that generates the interrupt. So the hardware detects a physical event occurring. Okay, the hardware of your microcontroller detects a physical event occurring. Hardware of your microcontroller is, for example, your ADC detects the ADC conversion has completed, or your GPIO peripheral detects that there is a external transition of a signal high to low or low to high, or your microcontroller timer, the hardware timer, it has timed out either underflow or overflow timeout already. So all these events, they will generate an interrupt. We call this event triggered interrupt. Okay, time triggered interrupt is an interrupt that is generated periodically after a certain amount of time. Normally, we program timers to generate time triggered interrupts. Okay? And interrupts, as you know, when an interrupt signal is generated, or the processor will immediately run the ISR code immediately with minimal delay. There is some delay, but that delay is deterministic. We can calculate the delay, right? For ARM microcontrollers or ARM processors, you can calculate the delay. The delay is exact. For example, in Cortex M processors, or in Cortex M processors, right? You got Cortex M0, M0 plus, M3, M4 is fixed. M0 is 16 cycles from the moment that the interrupt signal is detected, right? That means the moment that the interrupt is pended. You know, interrupts got interrupt flag, right? Interrupts, they got their interrupt flag, the pending status. So the moment that bit is set to 1, the delay from the moment the interrupt flag is set to 1 until let me just make this scrolling, until the ISR is executed, until the first line of code in the ISR is executed. This delay from the moment the interrupt flag is detected until the first line of code in ISR is executed, this delay is deterministic, right? It's fixed. For Cortex M3 M4 is 12 processor cycles. Okay, it's fixed. Right. So the processor responds. The processor responds as soon as possible to interrupts with a fixed delay. Okay, so when the processor is responding to interrupts, it's running the ISR code. You say the processor is in the foreground, in front, running the ISR code foreground. if there are no interrupts to process, then the processor is running the background code, and the background code is the super loop code. So what we're actually doing is we normally put the time we put the time critical code right in ISR, and we put the non time critical code in the super loop. Okay, time critical means time critical time critical means the CPU must respond within a certain time frame. So you say there is a deadline for response lah. Okay, you say there is a deadline for response. Okay, and a system that can do this, we call it a real-time system. Okay, a real-time system is not a system that's very fast. A real-time system is just a system that produces a response within a guaranteed response within a certain time frame or deadline. Okay, it's guaranteed that if the processor receives a certain input, it will respond within 1 millisecond. If it's within 1 millisecond, uh, then it's real time. But if it's after 1 millisecond and you say the system has failed, it's no longer a real time system. Okay, so if this deadline is very tight, the processor must respond within a very, very short time, then we call that time critical. So time critical, the processor must respond immediately. We put it inside ISR, we make it an interrupt. Okay, while those non-time critical can be delayed lah, no bad consequences one. Then we put it inside the background, the super loop. Okay, so this is how we handle. So this is describe how a super loop program structure handles time critical and non-time critical program functions, right? So you will put the non-time critical or inside the background super loop code, and the time critical or you will put it inside ISR code. Okay. Now, if uh, if you see this problem comes in when we need to do a real-time system, a multitasking real-time system. Okay, the problem is when we need to do a multitasking real-time system. That means we have to satisfy deadlines and we need to do many tasks at the same time. Okay, so foreground and background at some point may not fulfill your requirements anymore. So our best solution to this type of problem, multitasking real-time system, is currently using an RTOS. Is currently using a real-time operating system. But there are advantages and disadvantages. RTOS is our best approach at guaranteeing real-time response for multitasking systems. But the disadvantage is you need more memory and there is overhead. Okay, overhead means the processor has to spend a lot of time running the task manager code, which is not useful for your application. You write your application code to do some useful functions, right? But the task manager needs to run to switch between your threads. And when the task manager code is running, it's not doing anything useful for your application. Right? It's just switching threads. So we call that overhead. The cost that you have to pay, processing power that you have to pay, which is not really contributing to your useful application function. Okay, so super loop, of course, is the simplest. Foreground background is slightly more. RTOS has the most overhead. Okay, so you have to choose which one you use. You want based on your application. Okay, so that's the first question. So you can see that this is actually just understanding. You need to understand the problem. Okay, right. So you can answer in your own words. This is just a suggested answer. All right, now let's look at the next question. We'll just discuss two questions. Then we look at the exam type. Let's look at the next question, right? Okay. So the next question now, when each task is allocated with its own limited stack space, when each task or thread, we give it its own limited stack space. Limited. How limited? We can set this. For your example, normally default size of thread stack is 200 bytes, right? As you can see here, you remember this all. So each thread has its own stack size, okay, ending with the overflow protect pattern. So we can define this size, and normally it's not very big because threads don't use a lot of memory one. Basically, threads they just need 64 bytes for context to store their context. Okay, the 16 CPU registers. Each thread needs to save its 16 CPU register values that it is using. So that is 64 bytes minimum. If you don't have any local variables in your thread code, you didn't create any local variables, you don't call any functions, so you just need 64 bytes. Okay? But the main stack is a different story. The main stack is a different story. You see, threads use process stack. You have one process stack or thread stack for each thread. The operating system, on the other hand, operating system and interrupt service routines they share the main stack. The operating system, as you know, operating system code is all inside the NSV, sysdig, and SVC exception. All operating system code is inside these three handlers. Okay, they are exception handlers. And then you got all these interrupts. So they all have different priorities. So if they all happen at the same time, then you need to do interrupt nesting. And every time you have interrupt nesting, you need to save 8 registers into the stack. Okay, you need to save 8 registers into the stack. So let's say you have 3 levels of interrupts, different priority. So if all 3 come at the same time, you need to have 3 levels of interrupt nesting. So the main stack needs a lot more memory than threads. Okay. Now let's say the processor is now executing thread 1, the code for thread 1. Let's say imagine the processor is now executing the code for thread 1. Okay. An interrupt happens. How is the stacking? Where does the registers get stacked into? Now, if the processor is running the thread code, all right, and we are using the process stack, so when an interrupt comes along, the 8 CPU registers will be saved into the thread stack. It will be saved here. And then the processor will then go to the interrupt service routine. When the processor goes to the interrupt service routine, it will switch to use the main stack. Okay? If you are running thread code, when an interrupt happens, you will save 8 registers into the thread stack first. Which 8 registers? These 8 registers. Right? When an interrupt is detected, your processor will save these 8 registers into the current active stack. So which is the current active stack? The current active stack is the thread stack because processor running thread code. So the current active stack is the thread stack. So when an interrupt comes along, the 8 CPU registers will be saved here. Then the processor will go and run the interrupt service routine. When the processor runs interrupt service routine code, everything will be saved into main stack. It switches to use the main stack now. So if another higher priority interrupt comes, you have interrupt nesting, then the automatic register stacking will go into the main stack now. Okay, so this answers this question. When each task is allocated with its own limited stack space, so the task its stack space is quite limited, 200 bytes. Okay, stack overflow may occur because of stack nesting. In designs with complex ISR, if you have designs with complex ISR, that means you have a lot of different interrupt priorities. Let's say complex interrupt service routine. Let's say you got 10 different levels of interrupt priority. If all 10 interrupts happen at the same time, you will have 8 levels of interrupt nesting. Then you will use a lot of stack space, right? So stack overflow may occur in the thread stack. If we use the thread stack, so how does the ARM architecture handle this? You already know the answer. That's because the ARM architecture does not use the thread stack when running ISR code, right? The ARM architecture uses a separate stack for interrupt service routines, the main stack. The architecture doesn't use thread stack when running interrupt service routines. It uses the main stack. Okay, so the tasks that don't need additional stack space for interrupt service routine, you don't need it. Okay, just now I explained here. When interrupt comes along, you only stack one time here, just one time only. 8 registers, 32 bytes, just one time. Then if there are any interrupt nesting, they'll all happen here. Okay, so this is how ARM handles this. That's why the main stack, the calculation from the main stack is different from the thread stack. Right? As you have seen the exercise earlier, you have already done the exercise. This exercise. You calculated the thread stack size, right? And then there is a different method to calculate the main stack size. This is the main stack size. You use a different method to calculate the main stack size. You have to take into account all the different interrupt priorities and the maximum level of interrupt nesting to calculate the maximum size required for the main stack. Okay, right. So just want to point this out here. Okay, so these questions are quite theory based. Right? You need to understand how the architecture deals with operating systems in order to answer these questions. Okay, all right. So now you can try this out. The answers are all here. They are very short, simple answers. All right, the questions are straightforward. So I'm going to give you a exam type question now. Right, this is an exam type question. Again, this is not a full 25 mark question. This is only part A and part B. Right, so let's take 15 minutes to do this. Right, let's take 15 minutes to do this. So now it's 4:30. So let's discuss this at 4:45. Okay, let's discuss this at 4:45. Okay, so try this out now, and we discuss this at 4:45. Now, uh, try this question really very seriously. Right, just treat this like it is a final exam question, and then see how you score. Okay, we will discuss at 4:45, so you can try it now. Okay, everyone. Right, everyone. So it's time to discuss our question, right? So usually at this time we will say, okay, everyone, please stop writing. Now uh, we will discuss the answers. Okay. So let's look at question A first. Let's look at part A. So we have table A. It's showing us uh, three functions. Three functions. So we got three functions. Task A, task B, and task C. There are three functions here that we need to execute using the RTX. Okay. So these three functions, if you want to use them in your programmer, you will need the function prototype and you will need the function body, right? Okay. So the function prototype is in task.h. So we need to include this lah. And the function body is in task.c. So we need to add task.c to our project. Okay. Now let me give you an explanation of what is this task, this header file .h and .c file. Let me give you an example of what this is. Okay. Let's say let's look at this example here. Okay. Let's say I have a LPC 1768 microcontroller. Okay, I have this microcontroller, and then I'm connecting port 1 bit 18. Port 1 bit 18 now, I'm connecting it to a LED. Okay, so I want to write a program to turn off, on and off this LED, on off the LED every 100 milliseconds. Okay, I want to write a program to do this. Okay, so let's write the program. Now, first of all, I have to include L lpc17xx.h. Okay, so why do I need to include this file? Because I need to access the GPIO port, right? This is your uh, GPIO port. I need to access the GPIO port, the FIODIR register. I need to access the FIODIR register. So your FIODIR register, you got bit 0 to 7, bit 8 to 15, bit 16 to 23, and bit 24 to 31. So this is at 18. So 18 would be here. This is uh this is port 1 bit 18. So I need to put a 1 here. I need to put a 1 there to make it port 1 bit 18 to make it an output. I need to put a 1 there. So how to access this? I have to use the pointers inside this header file. That's why I include the header file. Okay, so I got my header file already. Now I need to write some functions. So I need to write the function prototype first. So my first function is, okay, I call it LED init. LED init. So I need one function to initialize the LED. I need one function to turn on the LED, and I need another function to turn off the LED. So I need three functions. Okay, that's all I need. Now I can start writing my main code already. int main void. Okay, I start writing my main code. So my main code, first thing I do is I call the LED init function. And I can call it, why? Because I already created the function prototype here. That's why I can use it here. If you don't have the function prototype and you call the function without declaring it first, you get an error. So no problem already. I already declared here with function prototype. Okay, after I initialize the LED, then I'm going to have my usual super loop. And inside my super loop, I'm going to turn on the LED. Okay, I need to turn it on for 100 milliseconds. So the simplest way to do it is I just call the sysdig config. I just call sysdig config. Then I just have a zero point 0.1 times system core clock. 0.1 times system core clock. Okay, so I have a 100 milliseconds delay. Now, I have to wait for the 100 milliseconds delay to elapse, right? Then I'll just use underscore underscore WFI. Wait for interrupt. So I wait for the interrupt. So if the interrupt happens, then I will need to run my sysdig handler, right? Okay, I need to add my sysdig handler. So I just, this one, this whole thing, I just pull it down a little bit. I need to write my sysdig handler. Okay, I need to write my sysdig handler. So my sysdig handler, I put it here, void sysdig underscore handler. uh void nothing. And then this is a dummy It's a dummy handler. I don't put anything inside. Why? Because I configure the interrupt to be generated after 0.1 second, after 100 milliseconds. So after, then I put the processor to sleep. So after 100 milliseconds, the interrupt will happen. Processor will wake up. He will come here, do nothing, and then return back. I just want it to do nothing here. If you don't write this void sysdig handler, your processor is going to go to the default sysdig handler and then stuck there forever because there is a forever loop inside the default sysdig handler. So I have to override the default sysdig handler with this sysdig handler, which got nothing inside. So I come back here. Okay, so I on the LED for 100 milliseconds already. Then I need to turn off the LED for 100 milliseconds. So I turn off the LED for 100 milliseconds. Uh, I need to um, delay lah. So this is my delay. Okay, right. So I delay for 100 milliseconds already, and that's all. So I look back, and this is my whole program. But you see, this way of programming, this way of programming, I cannot reuse the code. When I look at this, I realize that, oh, actually I wrote some nice functions here. Oh, I need to write I need to finish writing my code first. My code not yet finished. I need to write the code for LED init. I need to write the code for LED init. So LED init, what do? I have to go to the LPC underscore GPIO1 and which one I need to use? FIODIR. I need to use FIODIR 2 lah, right? Is equals to 0x 4. Why 4 lah? Because this is FIO0, FIO1, this FIO2 ma. FIO2 I put a 100 there. 100 is 4 lah. 100 is 4. Okay, that's all. I finished initializing my LED already. Then the next thing I need to do is I need to turn on the LED. So LED on. Okay. So how do I turn on the LED? I just use FIO. I just use FIO set. No? So LPC GPIO1. I just used FIO set 2. Just put there 0x04. So I turn on the LED already. And then how do I turn off the LED? So same thing lah. I do void. Okay, LPC GPIO1 FIO clear. FIO clear 0x04. Okay, so I have written all this code already. It's very nice. I can control the LED already. So I'm thinking, uh, I think or maybe next week I might do something similar. I might do a project like this. So I spent some time to write this code already. I want to save it so that I can reuse it next week. So what do you do? Okay, what you do is you cut this out. This one you cut it out, and this one you cut it out, right? So you paste it in this file. I'm going to call this file. I'm going to call this file. I'm going to call this file led.h. led.h. Okay. So I'm going to copy and paste this here. I'm going to copy and paste it here. Okay. So I'm going to this one cut and paste. I'm going to cut this out and I'm going to paste it here. I call this led.h. Then all I need to do here is what I need to do here is instead of having this, I will just write here hash include led.h. So what happens when you include a file? When you include a file, you are actually copying the entire contents of this header file and pasting it here. Okay, so instead of writing the function prototypes here, I put the function prototype in this led.h, and then I just put your hash include led.h. And then similarly, I'm going to have another file. I'm going to have another file. This file, I'm going to copy. I'm going to copy. Oops. I'm going to have another file. Okay, and then I'm going to copy all this one. I'm going to copy it inside here. Not copy. Cut and paste. I'm going to cut them out of the main.c. So this is my main.c. Okay, let me draw a box around this. This is my, oops, this is my main.c. So this whole thing is this whole file is my main.c. So my main.c, I cut out the function prototypes, I paste here, okay, and then I cut out the function body and I paste here. So the code for the function body, I call it led.c. Okay, and together these two files, right, is called the led library. So I've created the led library already. The header file contains the function prototypes, and the .c file contains the function code. Okay, I can reuse it in my future project. How I reuse it in my future project? Let's say next week I do a project. I want to use LED function, so I just put hash include led.h. Right? Then I can use all the LED functions already. And make sure that you add the led.c, this file, add it to your project. You don't need to add led.h. Just make sure that in your project folder, just make sure that, okay, this is your project folder. Okay, this is your project folder. Just make sure that inside your project folder, you have all the files that you need. So what are the files that I need? I need main.c, led.c, led.h. Make sure all these files are you copy into your project folder. Then when you create a new project, you add main.c and led.c. You have these two files in your project. No need to add led.h, because when you press the build button to compile, your compiler will look for the header file inside the project folder. You look for it, so you'll find it. Oh, there it is. And then you'll copy the contents of the header file and paste it at the hash include line. The hash include line is actually telling the processor, please replace this hash include line with the entire contents of the header file that is to be included. So everything here will be pasted here. Okay. So this is called the LED library. Now, for your assignment tool, you need to create the LED library, right? This is what is known as, we call this modular programming. When you program, you don't chuck all your code into one single main.c. You split out your code into modules. So this is the LED module, right? Why is good? Because these files can be recycled for future use and they can be individually tested. Okay, so they are called modules. Now, you already have the PWM and the ADC and the UART modules. You already have the PWM, ADC, and UART libraries or the modules. So those you don't have to write. Of course, you can choose to write them also. I provide them to you so that you can choose to use the libraries I give you, or you can write your own libraries. Of course, it's better to write your own libraries. Okay, and then there is no LED library, so you definitely need to write this yourself. LED.h and LED.c. Okay, so that's what they are. Okay, coming back here. So that's what the task.h and the task.c is. Task.h is just having the function prototypes, and task.c is the source code. Okay, so how are we going to write this program? I want to execute task A every 1 second. I want to execute task B every 100 milliseconds. And task C, I want to execute it every 10 times B has executed. Okay, every 10 times B has executed, I want to do C. And this is their priority, normal, high, low. So let's see how it's done. Let's see how it's done. Right. So first, I have to include the operating system header file, right? cmsys.os.h, to use all those OS thread create, OS thread define, all this stuff. And then I have to include task.h because that's the function prototype. Then I can call task.a, task A, task C, and task B without errors because I already included the function prototypes here. Where are the function body? No need lah, because they are already added to the project task.c. Okay, all right. So I'm going to, in order to execute task A, task B, and task C, I need to create 3 threads. So I create thread A, thread B, thread C. So here I create OS thread create thread A, thread B, and thread C. Create the 3 threads. So thread A is very simple. I just call task A every 1 second, right? Because we are given the system tick is 1 millisecond. See here, is given that the system tick is 1 millisecond. So every 1 millisecond, we will have one system tick. Okay. Right. So task A will execute every 1000 system ticks or every 1000 millisecond. So task A will execute every second. Fine, finish already. Okay, how about task B? Task B. So I put task B inside thread B. Okay, task B will run every 100 milliseconds. Okay, done. But we need to do one more thing. I have to count how many times task B has executed. Because every 10 times task B run, I will need to run task C one time. Oh, I got a typo here. I got a typo here. So this one needs to be, should be 10, not 3. Okay, this should be 10. Okay. So now task B run already, right? Then I increment this counter I initialize to 0, increment it by 1. So if I reaches 10, no, then I will just reset I to 0 and signal task C to run. Okay. So you see task thread C, thread C is just waiting. It's waiting to be signaled. When it is signaled, then it will execute task C one time. So every 10 times that task B run, we will signal thread C to run task C one time. That's all. Okay, it's a very straightforward program. Okay, so you have any questions on this program? It's pretty straightforward. Maybe you want to print screen this. Just take a few seconds to print screen this. Okay, 5, 4, 3, 2, 1. Okay, done. All right. Now, no questions. It's pretty straightforward. Let's look at part B now. Okay, let's look at part B. Okay, let's look at part B. So part B says assess the accuracy of virtual timer. So the question is virtual timer accurate or not? If accurate, why? If not accurate, why? So you have to judge the accuracy of virtual timer. How to answer this question? Okay, how to answer this question? Now, just draw it here. So okay, let me draw a picture here. Okay, I'll just write here. All right, virtual timer, virtual timer, or okay, the timing of virtual timer is based on system ticks. Okay, the timing of virtual timer is based on system ticks. So let's say this is system tick. Okay, 0, 1, 2, 3, 4, 5, and so on, and so on. Okay, let's say so system ticks. Let's say at this point, right at this point here, I go and run OS timer start, OS timer start, right? Or is it OS start timer or timer start? I'm also not sure. OS start timer or timer start. Let me check. OS timer start, timer start. So am I correct? Timer start, timer start. I'm correct. Okay, so OS timer start, no? Then I just start, let's say timer one, timer one, I start it for uh, two, two system ticks. Okay, so OS timer start, timer one, two system ticks. This means I want to execute the callback function after two system ticks. I want to execute the callback function after two system ticks. So when is the callback function executed? Okay, so here you reach this point. Okay, one system tick already, right? Then you reach this point. Okay, two system ticks. Execute. So we execute the callback function. Execute the callback function. Execute the timer callback function. Okay, fine. Two cycles, no problem, right? Now, but what if you're here? What if you execute the OS timer start function, you execute the OS timer start function, I want the callback function to be executed after two system ticks, but I call it at this point. So what happens? So here one system tick. And then here is one system tick. So what happens is you will execute the timer callback function. No? Is it two ticks? No, this is you execute the timer callback function 1.5 ticks later. Right? The blue one will be, this is 2 ticks later. This is what we want. But this one is 1.5 ticks later, so it's not good. Now, I give you the worst case. The worst case the worst case is when you go and execute here, right at this point. You execute the OS timer start. You execute at this point. So at this point, if you execute here, immediately it will be 1 tick later already. Immediately it will be 1 tick later. So then you get another tick. So what happens is I wanted the callback function for timer one to be executed 2 ticks later, but it actually gets executed. The callback function, the callback function executes 1 tick later. So therefore we have a worst case, not worst case error of one system tick. Right, this is the answer. Okay, so the question, assess the accuracy of virtual timer. Your answer is because virtual timer is based on system ticks, and you can call the function, the virtual timer function at any time. So this will cause a worst case error of one system tick. Worst case, you won't have more than one system tick. So your error will be between 0 to 1 system tick. Okay. All right. So any questions here? Any questions? No questions? Okay. So you can print screen this if you want. Oh, let me show you the answer. So the answer is here. Just scroll to the answer and you can print screen if you want. So this is the text answer. Just now that one is the picture answer. I prefer picture answer. It's easier to see and understand. But this is the text, so it means the same thing. Okay. All right. You can take a few seconds to print screen this. Okay. So okay. If no questions, then we will stop here for today. Thanks everyone for coming and have a nice weekend. Yes, Han Xiang, you got a question about the programming? Yes, what is your question? What is the loop? What is the for loop purpose after OS kernel start? Oh, okay. Now, you see, there is something interesting about kill RTX. Okay, there is something interesting about kill RTX. Normal RTOS, right? Normal RTOS, they don't have any threads one. Okay, normal RTOS that do not have any threads. You have to initialize the kernel and then create the threads. Once the threads are created, or when you start the kernel, the threads will start to run. Okay, I repeat again, normal RTOS they do not have any threads by default. You have to create all the threads. So you have to initialize the kernel, you have to create the threads, and then you have to start the kernel so the threads will start running. Okay. Now RTX, this operating system, kill RTX is slightly different. The main function is actually your first thread. Okay, the startup code, when you turn on the microcontroller, or the startup code of the operating system, it will automatically start the kernel, create the main function is your first thread. Okay, that means you can actually delete OS kernel initialize and delete OS kernel start. Why? Because the kernel has already been initialized and started before you run the main function. Okay, the startup code already initialized the kernel and started the kernel and then run the main function as your first thread. Okay, the main function is your first thread. So the purpose of the main function, your first thread, is you use it to create other threads. You use it to create other threads, which is why you see here, this programmer, uh, he used OS thread get ID to get the ID of this thread, the main thread. Once you have the ID of the main thread, you put it inside main ID. What you do with this, you see here, you see in thread B. In thread B, we terminate the main thread. Why we terminate the main thread? Because the main thread no longer serve any purpose. After you have created thread A, thread B, and thread C already, the main thread no longer serve any purpose. So you can terminate it, right? Now, this for loop here is actually an error trap. Type here. It's called an error trap. You want to trap errors. What is the error? Program execution is not supposed to come here. Program execution is never supposed to reach this line. Because when you start the kernel, right? When you start the kernel will automatically start running these three threads. So you will run thread A, then thread B, then thread C, thread A, B, C, and so on. You will never come to this line. You will never come to this line. So if you ever do actually come to this line, that means an error has occurred. It's called an error trap. Okay, you're not supposed to come here. In fact, program execution will never come here. Program execution will, after you have created the three threads already, right? The three threads will start running already. They will start running. Okay, you will never come to this line, this for loop. Okay, so if you do come to this line, then you are looping. The main function is actually running one. Is looping here. So is you're wasting processing power, right? That's why you terminate the main function. Okay, you see the main function after you do all this already, you come here, is not doing anything one. So you just terminate it, and then this main function will be gone already. So then you only have thread A, thread B, and thread C left. Okay, you try doing your section B labs, you see that there is a main function, right? Before you start your simulator or you look at your system thread viewer, you see there is a main function there. Let me show you. Let me show you. Let me close this project and I open one of your lab projects, section B lab. Okay, let me open one of your section B lab projects. Let's say multiple instance. Okay, let's say multiple instance. So I run this. I build this. Build this. Then we run it. We run it. Okay. Then I show you you see this one here. This is your system and thread viewer. System and thread viewer. Okay, let me zoom in a bit. Just zoom in a bit, then I show you here. Okay, you see this? This is your system and thread viewer. System and thread viewer. You see the main function now is actually a thread, right? It has normal priority and is currently running, right? Zero stack usage, so it's a thread. Okay. So what the code does here is you terminate it. Because the main function, after it does all these things, it's going to come here and loop here forever doing nothing. It's a waste of processing power. So you will keep coming back here one. After you run A, B, C, or you will come back to the main function one. So we don't want to waste processing power here. Just terminate it. Is that okay? All right. Okay. So no more questions, huh? Okay. Okay, you're welcome.